So introduction to base mapping datasets. Of course, we are running a planetary mapping school, but we need to know where to gather the data before starting to map. And to gather the data, I mean all the types of image data and topographic data that is available to us. There are many data repositories for visualization and download. They are improving and increasing throughout the years, but essentially they can be narrowed down to these ones. They are the PDS, Planetary Data System of NASA, PSA or PISA, it's the Planetary Science Archive, the Orbital Data Explorer, the Pilot, which is specifically related to planetary images, Astropedia with some high-level already processed products, and the software GMRs. But you can also visualize on the fly planetary data, especially for the Moon and Mars. I will not dive into Google Earth too much, but essentially, if you open the main interface, there's a small button here at the top with a small planet, and here you can choose Mars or the Moon. Then software will jump to the selected planetary body, and then you can choose to select some global maps, some colorized terrain, and so on and so forth. And then you can toggle on and off the products that you want to have. In this case, high resolution images of the Martian surface, CTX images, some spectral data, and so on, and some like good for outreach types of maps, such as the landing sites, position of the rovers, and so on and so forth. Another interesting one that I would like to demo for you is the NASA Tracks. NASA Tracks was growing very fast and very large through the years. And this is basically some trackings in the solar system. And you see that we have a lot of planetary bodies where you can just have some information that can be used for, again, outreach or general knowledge, but you can also go more in depth and download some data. And so I would like to show it to you. So this is the web page of the Solar System Tracks. You have your solar system here. You have some galleries, like feature of the month. Did you know? Some curiosities, some virtual reality libraries, layers of interest, some features. You can 3D print maps. You can visualize in 3D planetary surfaces, calculate stuff, calculate sun angles, and so on and so forth. If you click here on Explore Tracks at the bottom, you will see that you can explore basically most of the solar system planetary bodies. Let's say I want to go on Mars. So this is jumping me to Mars in its position. And I see an overview of Mars with some description. Okay, and a very nice 3D view of Mars. So I'm landing somewhere on Mars in a chaos terrain into a high resolution image. And then I can click and I can explore it. So this is opening the Mars track window. It can take some time because there are lots of resources that are going to be pulled from the web. So you have to be patient. And now you can have a tutorial. I will skip it for the moment. And here you have the Martian surface. So you have many, many options. Let me make it larger. Here in the top left, you have the data. These are all the types of data that you can have. There are some maps, there are some image data, some landing site data, and so on. Here are some layers that are stuff that you can add to the visualization of your map, and here are your downloads. But before, you can go to the right and see that, for example, if you zoom somewhere, like here in the Tarsis volcanoes, you can calculate the distance with a line. You simply drag a line, and you are provided with some distance. Super quick, super easy. But you can also calculate distance, of course, with a polyline, this way. Okay. And you can also calculate the elevation profile. Again, with a line, a polyline, or a freehand polyline. Let's say I want to make a profile along this line again, more or less. Here you get the distance, and again, you can submit it. And here you're getting your elevation profile. Here is telling you the type of data, MGS MOLA. You will see later what it is. And then you can simply go on your profile and you will see that the cursor here is appearing to calculate your profile. And you can export it into CSV or JSON to plot it into Excel or whatever you're using. There are other things. For example, you can calculate the sun angle. Let's say I want to see my illumination conditions at the top of my volcano with a point. I pin a point here. I want to see my sun angle starting from the 2nd of October of 2025. Sorry, it's the 10th of February. It's in reverse. To the 11th of February or to the 28th of February, for example. If I submit it, here I got my plot of the sun elevation angle in the Martian days. Yeah. Sun elevation, the angle and the azimuth of the sun. So how it has a variation with respect to the north in clockwise direction. And again, you can export it in CSV. You can generate a 3D print file. Let's say I want to 3D print my volcano. I can draw a rectangle. I can use it either STL for 3D printing or an OBJ. Okay, and I can submit it. And now my 3D printed files will be generated and downloaded here. In the meantime, we can go here and see how many base maps we can have. So we have a color base maps. You can toggle on the nomenclature, for example, like this. So you see more or less where you are located. And now my 3D printing files is in download. So you start to see some nice things. And then let's say I want to add some data again from Ascreus Mons. So, I have my file here. So I can go here. And this is my model. Let's see my 3D model. Okay. Very nice for printing and display and visualization. Okay. Here I can then, as I said, explore features. Okay. For example, I can add some layers or download some layers. This is the topography layer. I can download it like this or add to the download list. So I click here and the topography is going to be downloaded. So it's very quick and very effective. There is a global DEM again, so you can explore and then see the data for yourself, some thermal inertial data or global dust data. You can add it so you can see where is the dust on the surface of Mars, and so on and so forth. So you can see a lot of things, and there are also some layers, for example, hydrous minerals, the global geology, so a global geological map that again you can download. So this is very quick and very effective in terms of retrieving data and visualizing them very, very effectively. To go back to the other tracks, you simply close this window. By the way, you can also swap projection. You can go to North Polar map if you want to explore the poles, or you can go to South Polar map or to the 3D globe. To go back to the other tracks, there's the mole icon here of the solar system. You click and then you jump to the tracks, and so you can explore other things like small bodies, like, I don't know, asteroids like Bennu. You see where they are. You are provided with a shape model, and again, you can do the same type of things with the available data. Let's jump back to the presentation. The PDS. PDS is basically the global, super fancy big repository of NASA, where you gather all the data available from all the space missions that are related to NASA. It has an interface page where you can select the spacecraft here, the instrument, the target, product type, if it's I don't know, some images. or some spectra, or other types of data, and some product-related features like mass reconnaissance orbiter high-rise, mass science laboratory curiosity, image context, Cassini, and so on. So I encourage you to visit this one as well. Same as for ESA PSA Slice Archive, where, for example, you can gather images from the latest ESA missions like Rosetta, for example, or ExoMars. And the way it works is the same. You have many types of interface. My preferred is the map view. You click on the map and you gather lots of results. But one of those where I want to focus my attention the most is, again, the Orbital Data Explorer. And why? Because it's encompassing all the bodies of the solar system that we will explore within this school. It is essentially a part of the PDS Geoscience node. It's maintained in Washington University, St. Louis, and it's connecting all the types of data that are relevant for geoscience. This is why it's called PDS Geoscience node. So other types of data for astrophysics, or you will not find data from the Space Web Telescope, for example. But essentially, there's an interface, and you will get in my PDF lesson all the tutorial on how to use it. But now I will want to demo it for you. And so we will go here. Let's close menu, and we want to go to the PDS Geoscience node. So here you have all the planetary bodies that we will encounter this week. The list of supported missions and instruments. You will see some of them a lot during this week. Let's click on Mars again. And here you have a nice interface. And what we like most as geologists is to look at maps. So I go to map search immediately. I am provided with some base map. Here on the left, like in a JS style, you have the available layers, and here you have the available base maps at the bottom. Let's say I want to see my topography to understand better where we are, and I want to go somewhere here. And let's say I want to download some data about the Danielson crater. You will see this in the last day of the 3D geomapping activity and demo. And I want to see all the products that are within this area. If I select here, you will see that I can have a look at the instruments on board the Mass Reconnaissance Orbiter. Let's say I want to see high-rise images, the high-resolution images. My derived product can see whether there are some DTMs, so digital terrain models. I see there's one, except this is the one that you will see, in fact. Or if there are images, you see that there are lots of images. But what happens is that if I toggle this on, you will see all the high-res images throughout the whole surface of Mars. This can be quite heavy and time-consuming if you have a slow network. So my suggestion is to go here at the top, select display only products selected by area. And with the tools that you have here, you can simply drag a box. And once you have selected your area of interest, you can select the products that you want. And so there will be only those that are intersecting this square. You can also make a polygon, a polyline, etc. Once I have selected some products, I can go here and click to view. And this is a preview of all my products. And if I zoom in, you see that when I hover my mouse on top of one of these, this is highlighted in the map in black. Okay? I simply move my mouse and I see where it's physically located in the footprint of my image. This is a color high-rise image. If I want to check it before downloading, I can quick view. There's the button, quick view. I can click it. And the interface is opening. And I can see it, zoom in, and zoom out to have a quick grasp of what I will be seeing if I download this image. I can select add product to cart. Basically, we are going shopping for images now. Here you have some information like metadata, label, related products, and so on and so forth. Some ancillary files like, I don't know, shapefile footprints if you want to have them into your JS and so on and so forth. But that's it, more or less. So you can quick view all your images. So once you have selected those that you want, for example, this grayscale image and this color image, you see it's saying it's in cart. It's in the cart. So now I put those in the cart and I can move here in my download cart, select it. This is processing my request, so it's taking into account the flags that I've put into my interface before, and then providing me two things, essentially three things. How I want my download archive to be organized, the size of the download, and how much time it's going to take for them to process my request and to get the download link. In this case, I think it's taking a while. Okay, I get an error. Let's try again. But that's it, more or less. So at some point, you will see anyways in my shared slides what I'm talking about. Let's select an area, very small area, Mass Express or Mass Connected Orbiter. On CTX image. Let's say you want this, which is very small. It's in the cart. I can go here. And let's see if this time it works. If it doesn't work anyways, you have all the information in my PDF, which is going to be shared after this lesson. You will get here some options. You can provide, there's a field where you can provide your email. You type your email, you click, and then eventually, after a while, after they process your request, you will get an email with a link to download your data in a zip file or in a tar file, which is a package that you can then unpack and just load them into your JS. Today, this is not collaborating. So I would say we can move forward. This is, anyways, how to use it essentially. So base maps, display the products in the area, and then I can select an area with a square or with a polygon. And again, here I can change the projection, North Polar or South Polar. This is for Venus, Mars, Mercury, and the Moon. So let's move back to the presentation. The pilot. Pilot is not only related to Mars, Venus, Moon, and Mercury, but to all the solar system bodies for images. This is just for images. Whereas on the Orbital Data Explorer, you can also download the DTMs, and topography, and radar data, and so on. Pilot is just for images. And let's see Pilot in action. So here you have, again, a lot of images. Let's go maybe to the Moon. You have a preview of how many images they have been collecting in full time on the Moon. So it's 4 million images. If you click on the Moon, you can choose the instrument. Let's say you want to use LROC camera. So here is providing a huge list of LROC camera images. Only of this camera, we have more than 2 million images, 2.5 million images. I can click on the map. Here there's a map display. And let's say I want to go here in Tsiolkovsky crater on the far side of the Moon. I want to have a look at my central peak here. Okay. Here I have some tools that I can use, and I can draw a polygon around the central peak, for example. Double click to close. After I double click, it immediately pulls a request from the server. And it says I have 346 LROC camera images. Okay, all intersecting this polygon that I made. Let's choose one. For example, the first one. I have many buttons at the bottom. The first one is some metadata. The instrument, when it was acquired, emission angle, incidence angle of illumination, phase angle, the ground resolution, processing when it was acquired, the solar longitude, and then also the map projection for the system. You see that I have enabled the beach ball here, which is essentially how to show it on the map. You can click also on others. You can see them where they are located. If I click on this button on the small arrow, I will jump to a download page. Let's do it later. And if I click on the small camera, I can have a preview of the image, which is here. This is a bit less fancy than the one of Orbital Data Explorer, but still useful. And if I click on the small arrow, I can download the image. or I can select multiple of them. Okay. And here you see that I have selected 3 in this top right corner. There's other buttons, I can deselect them or select all of them. This is not advisable. You see how much time does it take. Let's deselect them and select just a couple of them. And here with this small arrow, I click and I can have different options on how to download them. First one is to have a CSV file with all the metadata information, including the URL where I can download the image. If you are good in working with the terminal interface like wget or command line features, you can download the bash script file with the wget calls, or you can go on the projection on the web, which is a service that is projecting and working the images for you, and then there you will get an email to download your finished products, which is essentially what you have here. This is the projection on the web. You will jump to this interface here on the right, where you can choose a processing template. You will get a summary of the files to process, the label, the projection you want to have, like rectangular, sinusoidal, polar, all the projections that Giacomo showed you. The extent, if you want to crop it, if you don't want to crop it, if you want to remove the background, if you want to keep the background. The file format, GeoTIFF, 8-bit or 16-bit or 32 bits if you want to stretch the images to highlight something that is in the shadows, and so on. And then you can add the job. This is added to their queuing system. You can provide your email, and then you will get the download links eventually after a while. So this is very cool and very nice because this is basically bypassing all the bulk work that you have to do to download the raw data and process the raw data. In fact, what I didn't show you is that here you are downloading the raw data. So after that, you will need to process them via Iris or other softwares, which is maybe good for specific applications, but you can avoid it by using the pilot. Then there is Astropedia. Astropedia is maintained by USGS Astrogeology. You will have a talk later today from James Skinner from USGS Astrogeology about planetary maps and all the infrastructure, how it works. And essentially, this is different because it's not gathering data from all space missions, meaning that you can download a single image from a single camera on a specific location, or download 3-4 images to make a mosaic. But here you have high-level products. You have high-level mosaics. You have already processed data, already processed topography, base maps, geological maps, historical maps. So I will suggest you to have a look, and let's have a look together. This is the interface of Astropedia, and you see that there are some picture collections, and here you have the solar system bodies, like small bodies, Venus, Moon, Mars, Mercury. Let's say I want to do something on the Moon. I click on the Moon, and here the table of content is changing. For example, here I have provided the unified geological map of the Moon. So I click here, I jump to this page. I can see a sample, or I can download it. I can download it in PDF format. Let's see if I can see a sample of it. Okay. Here there's a description on how it was obtained, the updates in new versions, the references, including publications, the purpose, and all the contact and distribution, including metadata, dates, how it was produced, which type of data, the point of contact in terms of who you want to contact if you want information about it, how it was processed, and then some geospatial information. And here you have ancillary data. For example, you can download it in raster format or in GIS format. And here's some possible related products. For example, an older lunar geological map from 2013, and other types of maps. But if we go back, let's have a look. You can also download, for example, data. For example, del LRO, LOLA, Slenka, so laser data, for example, topographic data. Here again, you can see a sample and you can download the actual data. So it's here 11 gigabytes, so it's a lot. And here you have all the information useful for you. So it's a matter of knowing the types of data that you want to download. Here you can also select a target on these drop-down menus. Geospatial form if I wanted 3D, a database, a raster, vector, and so on and so forth, the type of map projection. This is basically filters of all the materials that are included here. Jumping back to the presentation, JMars. I will not demo the JMars, but you can download it at the address here. It's basically a sort of a JS system where all the maps are streamed into the system. You can use it into different planetary bodies, and you can do some basic mapping stuff. You can count craters, make polygons, and share it with the others. So it's a good way also to explore planetary bodies. Regarding Venus data, especially, you will mostly work with the SAR data, so synthetic aperture radar on board the Magellan mission. You will see it tomorrow, dedicated talk on how to read and interpret the radar data because they are quite peculiar and they're used for penetrating the clouds on top of the Venus atmosphere to see the surface. Mercury data. Here we have the Messenger Quick Map. Essentially, we will use data from the Messenger mission. Messenger Quick Map and Quick Map in general, they exist also for the Moon and Mars, are platforms that, sorry, my Zoom interface is, okay. You have a browser-based interface. You can change the projections again. Here you have the layers. You can search for, I don't know, hollows or other types of features on the surface. You can zoom on them. Yeah. You can add a lot of these layers. You have a lot of these products that can be visualized basically on the spot here. I will demo the same for the Moon in a while because we have the same system also for the Moon. But before, I want to just give a brief overview of the types of data that you will enter on the Moon. Lola, and Rock, and Selen-Kaguya. Here you can access it, as I said, on Google Moon, ODA, Pilot, Quick Map, and so on. The Reconnaissance Orbiter was launched in 2009. It was a very successful mission. It was carrying lots of important instruments, but for us, the most important are the narrow angle camera, which is called NAC, Rock NAC, taking images of 0.5 meter resolution, very, very beautiful images. We'll work on those in the next few days. Here you see some details of some boulders at the top of the Tycho crater that were ejected and then bounced back after the impact happened. This is basically the size of a flat. And here you can see some quick map demo on the Moon. Here you can change projection. Let's say I want to go to the South Pole because I'm interested into the exploration of the South Pole. I want to see what are the Artemis landing sites. These are the candidate landing regions. Let's focus, for example, here. And here I want to know other things. For example, I want to know if there's some titanium abundance or the illumination map. Here I will get all this type of information. If we move back to the equidistant cylindrical map, and let's go to Copernicus crater, I can also see some geological features. For example, the unified geologic map that I showed before. With, if I click on top of it, the legend. Yeah. So I suggest you to explore these functions. You can also adjust the transparency and also other layers. For example, I don't know, the Clementine data or the color ratio for the composition variation. And here again, if I click on top of it, I can adjust the transparency. Or I can see, I don't know, the titanium abundance. let's see if I'm able to get it on the lunar surface. Weight percent. Here is my titanium abundance. And again, I can play with the overlays. I have my scale of color here and all the description of this data. Eventually, I can also download some data. So I can go here and I can use a region of interest, for example, a circle. I click and I drag, I draw a circle around this crater, and here I get some features. For example, the coordinates, I can inspect it. So I can, in line of principle, download all the data that I have here in a sort of a downscale format of about 256 by 256 map pixels, where I can have a sort of a combined raster with all these layers that I have here in order to have a look at all these illumination conditions, mineral maps, and so on and so forth. This is basically a summary product, but I can search for product also here. I can search for, I don't know, not DTMs, so topography, okay? I have these here in this area. Or I have feature mosaics, yeah? Here again. Or regional mosaics. So I can download already mosaic data. Let's say I want to download this mosaic that you see here on the left. I click on top of it. It's added to the map. And I can use it. You can also download products, as I said before. Here I have some NAC images. Let's see if they can get one. I choose this, I click on this link, and then I'm jumping to this link, and I can see this NAC image. I can see it. I have all the information, and I can proceed to download. So you see that there are many ways to gather the same type of data of information. So it's a matter of which one you prefer, and they differ more or less for some features. Mars data. For Mars, there's a lot of data everywhere. These are the missions that are being active in the recent past or still active nowadays, especially Mars Reconnaissance Orbiter and TGO, Transgas Orbiter. And these are all the points of access that you can find. We will essentially use for Mars the Mars Orbiter camera, which is a panchromatic camera of 1.5 to 12 meters per pixel with this type of coverage. So you see that is a targeted camera, very high resolution, so you cannot cover the whole surface of Mars. This is where you can gather data. Thermal emission camera, where you can see in the day and the emission in the night. So you can play with these two layers and see how the heat is being emitted from the surface of Mars. And the bright areas are those that are emitting heat throughout the whole night. And this is telling you whether you have loose material or exposed rocks that are more compact. So they are material contrast. And you can play with those two to highlight morphology or to highlight changes in composition or granulometry. High-resolution camera from ESA, HRSC, and more than Mars Express. Beautiful data products, both in topography and color, with a very good coverage. CTX contact camera, 6 meters per pixel, very beautiful mosaics that are mostly used for doing mapping nowadays, together with HRSC, with a global coverage. And HiRISE, which is the one that we will use in the next days. It's 25 centimeters per pixel resolution, able to produce color images in 4 filters, also in the infrared, and stereoscopic capabilities, so topography with 1 meter pixel resolution. Here you have a demo of how you can see some data products, like surface changes at very high detail with the Earth cells or in the recurrent slope lineae. And here, if you look at this image, you can see the Curiosity rover here, where I have my mouse, and all the rover tracks. We will use this data to carry out our 3D activity in the last day. This is a demo of how it works and it looks like when you have a topography with the photo image draped on top of it. And in the website of HiRISE, you can download pre-prepared topography because it's quite heavy and time-consuming to produce some. And here's some map coverage. You see they are so big and so high resolution that the data volume is so large that you have to target this type of observations on the Martian surface. We also have ExoMars TGO Cassis stereo in 4 colors, same colors as HiRISE, that go from the visible to the near infrared, and with a broader view, so you can give a context to the smaller, narrow, targeted HiRISE images, and with beautiful colors and topography. And here's some coverage that is improving and augmenting through time. Difference is in resolution. High resolution is for high scale studies, high detail studies, like the one we will do in this school. Lower resolution like CTX is good anyways to map the most prominent features, but not the very, very fine details like the small layers, the small boulders, the ripples from the dunes, and so on and so forth. Whereas if you lower the resolution to half of this one, like 12 meters per pixel for the HRC, you will get a broader context, but you lose the details. And of course, you have to zoom back if you want to use thermal emission data. So it's also a matter to compromise what type of objective you have to achieve, the amount of data you are downloading, and the resolution of such type of data. And this is how we organize our data most of the time. We get a base layer of low resolution with a broad topography. Then we get some image data or thermal data at the similar resolution. And then we increase the resolution in a pyramidal way. And then at spots, we will have our very high resolution images in the targets that we really want to see in high resolution. So this is a sort of a nested approach. And it also depends on the scale where you want to map. If you want to map a 500-kilometer volcano, I will not suggest to use HiRISE at 25 centimeter resolution, not even CTX or Cassis, but using HRC at 10 meters per pixel resolution, or even TIMEX at 100 meters per pixel resolution. It depends on the target and the scale of the target that you want to map. There are other tools that are specific for downloading the types of data. I will not use time on that. This is the multi-orbit mosaic of HRSC that are now composing some tiles to get huge big tiles of already mosaic data, also pan sharpened with colors. The Marcy service, if you are curious, here you can log in, create your login, register, and then you can go here, download some pre-processed data, and also request the production of stereoscopic DTMs for your needs. They are going to take care of it. You are going to receive an email with the link to download your custom-made topography. And then there's the Astropedia WMS. Note down this link. It will be anyways in my shared presentation. And essentially is the page where you can stream your data directly into your JS system. It has all the solar system bodies. There are links that you can use to stream those data in your computer without filling your disk space with lots of information. There is a tutorial on how to do that in my other presentation, and you will find it shared after this lesson is finished. In the program, you will see on top of my lesson, the name of the lesson is becoming an active link, and you can click and download it. Then there's Arrow Browser. This is taking into account a lot of information about rover images. Okay, on Mars, for example, you can see terrains. You can visualize terrains and download terrains. You can see rover images, and it's a really good source. But other good sources are the analyst notebooks. These are notebooks if you are interested in rover data, especially Mars rover data, but not only. You see there's also Apollo data or landers like InSight. Basically, you have inside their interface the whole path, base map, types of data, notes, information. If I don't know, the Curiosity rover extracted some drill cores, you can have a quick look of the photos of the drill cores, and you can do the same for Perseverance, InSight, the Opportunity, Spirit, L-Cross, and also the Apollo mission. Here is a demo of the interface. Let's go to, for example, Perseverance. You can create your account or browse anonymous. And then you can get started. You can click here. You have layers with some explanation. Map layer here. This is opening my map. I can make it full screen. And here's the path of perseverance. If you are curious, we made a full lecture about it in the school of 2023 about the landing site of perseverance. And you can see all of the activity that it carried out throughout its path. You can click on top of them, have some information, the plans of the rover, the types of instruments that they were used, image mosaics, for example, here. And you can have a look of all the images of the rover. This is a very powerful and beautiful resource. It's a sort of a rabbit hole for the rover lovers. And finally, there's the Mars Life, specifically for Mars rovers. And this is where some of the data of the last day's activities were gathered. And you can explore the surface of Mars, where the rovers traversed into interactive 3D panoramic views. So I will suggest you to have a look because it's really interesting. This was a very, very quick overview, and I have not the mission of having given you all the information that one needs to know, but at least you know where to go and look for resources. And anyways, you will have a more complete view when you will see the uploaded PDF lesson for you to as a guidebook. Anyways, the mapping projects that we will use for the school are already pre-prepared using the data that you have seen here in this presentation, and we will use them throughout this week.